Hello, we're going to look at Unit 1, Lesson 2. We are on page 13 in our workbooks. So at the bottom here, I'm going to let you answer number 1 on your own, and I'll summarize it a little bit for you, but you can read it. Basically, it talks about how when you're learning to drive, if you are driving at a faster rate, you should leave more space between you and the car in front of you. And it talks about driving on the freeway. And so question 1 asks about different factors that you think could influence how far a car travels after hitting the brakes. So I'll let you answer that one on your own, and then when you're ready, turn to page 14. Some things that I think affect the braking distance could be any sort of friction, how good your tires are. They call them bald, so if they start wearing down, they don't have as much grip, so less friction. The weather can affect it. If it's raining, it could make it a little bit slipperier. So lots of different things that you could say in number 1. So now we're going to look at some math behind things. So here there's actually been quite a bit of experimental work done, mostly by police departments and insurance companies, to be able to mathematically model the relationship between the speed of a car and the braking distance, so how far the car goes until it stops after the driver hits the brakes. Imagine your dream car. Maybe it's a Ferrari 550, a super fast Italian car. Experiments have shown that on smooth, dry roads, the relationship between the braking distance and speed is given by d of s equals 0.03 times s squared. And our speed is given in miles per hour, and the distance is in feet. I want you to pause the video and answer questions A through D, and then when you are ready, resume the video and I will go through all 4 parts. All right, so for part A, how many feet should you leave between you and the car in front of you? We are given our speed, so we're going to plug that in for S in our equation. So I have my distance is equal to 0.03, inside parentheses, my speed of 55 miles per hour squared, and I can type that right into my calculator. So I have about just under 91 feet. So 90.75 feet. So if we're going 55 miles per hour, that's how much feet we need. The next one, what distance should you keep between you and the car in front of you if you are driving 100 miles per hour? So we're still plugging in 100 into our speed, into our formula. So we would need 300 feet. If an average car is about 16 feet long, about how many car lengths should you have between you and the car in front of you if you are driving 100 miles per hour? Well, we know it's 300 feet, so I can take my 300 feet and divide that by 16. When I do that in my calculator, I get 18.75. So that's about 19 car lengths. So that should give us a nice visual. If we're going 100 miles per hour, which you shouldn't, that's over the speed limit, we need about 19 car lengths. That is a lot of space between us and the people in front of us. So it makes sense to a lot of people that if a car is moving at some speed and then goes twice as fast, the braking distance would be twice as far. Is this true? Explain why or why not. So we have some information up here that would help us understand that it is not true. So 100 isn't quite double what 55 is, but we can see that 300 feet is way more than double this 90 feet. And if we wanted to test that, let's actually do 50 miles per hour. So I'm going to plug in 50 into my equation. So if I'm going 50 miles per hour, I would need 75 feet of braking distance. If I double my speed, and people think that my braking distance would double, that would be about 150. But we know that if we double our speed, it's actually 300 feet. So there we have some proof that no, that is not true. And I'm going to let you explain it in your own words using what I mentioned or our information above. So for number 3, we are asked to graph the relationship between the braking speed or the braking distance and the speed. So I'm going to make a little table here. My input is my speed and my output is my braking distance, because in part A and part B, we were plugging in speed into our equation. So that's our input, our x values. So let's do maybe like 20 miles per hour, 30 miles per hour, 40, 50 we just did in the calculator, and we got 75 feet. Let's jump to maybe like 80 miles per hour, and we already did 100 miles per hour in part B. So 100 miles per hour was 300 feet. So let's take a second to figure out the distances for those speeds. Whoa. So 20 miles per hour needs 12 feet. And if I'm going too fast, feel free to pause the video so that you can catch up. But right now we're just plugging them into our equation. So now that I have my table, I want to go ahead and graph this. My inputs or my x values was my speed, so I'm going to label my x-axis, and then my braking distance or my stopping distance is my y-axis. I'm going to do a scale of 10 for my speed, but I'm just not going to label every one. So I have 10, this would be 20, 30, 40, 60, 80, 100, and that's actually where I stopped. And then for my braking distance, because we get up to like 300, I'm going to do a scale of 25. So I have 25, 50, 75, 100, 125, 150, 200. And again, I'm just alternating the ones that I'm labeling. So 250, 300. So I'm going to plot these points on my graph, and I want you to do yours, and then we can see how we did. I'm also going to include 0, 0, because if I'm going 0 miles per hour, I need 0 feet to stop the car because it's already stopped. All right, so my graph looks something like that. I'm going to set this graph off to the side, and I might get it back out to talk about different things. But we're going to move on to page 15. So on page 15, looking at number 4, it says, according to the Ferrari company, the maximum speed of the car is about 217 miles per hour. That's my maximum. Use this information to describe all the mathematical features of the relationship between braking distance and speed for the Ferrari modeled by the function d of s. Your answer should include the domain and range, any intercepts, max and mins, and the intervals of increase and decrease. So I do want to put my graph kind of next to this page so we can see it. So I'm going to try to scoot this over a little bit. I just want it, I don't know if we can see that real well. Actually, I'm going to fold it so I can have it underneath here. So when we're looking at our domain, we're looking at all of our x values, how far left and how far right our graph goes. So looking at my graph, the furthest left has an x value of 0. I cannot go slower than 0 miles per hour. I can't go in negative speed. That would just be like in reverse, which I'm still going the same speed. So 0 miles per hour. And then the maximum that my speed can be, or the furthest to the right, I'm actually given in my scenario. So the maximum speed is 217, which is the maximum in my domain. And I'm actually going to label my domain here as my speed. So my lowest speed and my highest speed. Then for my range talks about the output values or my Y values, and we're looking at our braking distance. My range is dependent upon my domain. So when I am going a speed of 0 miles per hour, that corresponds to 0 feet. So I know the lowest value of my range is 0 feet. Yes, I can look at my graph, but these numbers are paired together on my graph as well. Then I'm going to look at the maximum value that my range can be. So the maximum distance that I would need would correspond to the maximum speed. So I actually don't know what that is. I'm going to have to do some side work here. So I'm going to take my equation and I am going to plug in a speed of 217. That's my maximum speed. So whatever distance I get here would be my maximum distance for my range. So I'm going to type that into my calculator. And I get 1,412.67. So I'm going to write that here. And then for my range, that'll be the maximum braking distance that I would need because it corresponds with the maximum speed that I can go in this car. So then for my intervals of increasing or decreasing, if I look at my graph, my line is going up as I go from left to right the entire time. So it is increasing on the entire interval of our domain. So we can say increase on entire domain. And our domain is from 0 to 217. My minimum is the lowest point, so my minimum is 0, 0, which makes sense because I had 0 miles per hour. That corresponds with 0 feet as my lower bound for my domain and range. That goes with that point. My maximum is a speed of 217 that requires a distance of 1,412.67 feet. So this coordinate point would be my maximum. The X value is the ending of my domain, and the Y value is the ending of my range. I want to explain this as well. So here I know 0 miles per hour, my X value, requires 0 feet. And then for my maximum, 217 miles per hour requires 1,412.67 feet. Just to kind of explain what those points mean in context of the problem. So I'm going to move my graph off to the side now that we are kind of done with that one for now. I want you to take a second to pause the video and answer question 5 and 6 on your own, and then when you're ready, you can restart the video. So question 5, we are told that there was a cat and she missed it. Good. When she got out of the car, she measured the skid marks left by the car, and she knew that her braking distance was 31 feet. This time, if we have our equation, we are given our distance, so we're going to plug that in for D and then solve for S to see how fast she was actually going. So I'm going to plug that value in. To solve for S, I want to divide both sides by that 0.03. So they cancel out on the right-hand side. 31 divided by 0.03 is 1,033.3 repeating. I guess I did that in my calculator there. And then to get S by itself, I got to get rid of that square. So I'm going to take the square root of both sides, and I get a speed of just over 32 miles per hour. So for part A, she's going approximately 32 miles per hour. So in B, let's say she didn't see the cat until she was 15 feet away. What is the fastest speed that she could be traveling before she hits the brakes if she wants to avoid the cat? So here I'm going to plug in 15 for D and do the same thing. So I'm going to solve this for S, divide both sides by 0.03, and then I'm going to take the square root of that, and I get a speed of just over 22 miles per hour. So we're going to say approximately about 22.4 miles per hour. For number 6, you should have filled in the table there when you pause the video, and then I'm actually going to flip to the next page. So on page 16, for number 7, it says write an equation of the function s of d that gives the speed the car was traveling for a given braking distance. When it says given the braking distance, that means d is going to be our input, or like our x value, and then speed would be our output. But we know in our original equation we had speed as the input because that's what we were plugging in. So I'm going to remind myself what that equation was, but now I want to solve for s. So I'm going to make a little note here. So I'm going to solve for s. To do that, we're going to do what we just did. If I want to get s by itself, I still want to divide by 0.03. And I'm going to continue it down here, even though there's words there. So I have d over 0.03 equals s squared. And then I have to take the square root to get s by itself. So I take the square root of the entire right side, and then I'm going to take the square root of the entire left side, so around that whole fraction. So that means s of d is going to equal the square root of my distance divided by 0.03. So number 8 says graph the function s of d and describe its features, including domain, range, any intercepts, maximums, minimums, or intervals of increasing or decreasing. So I want you to pause the video and try to answer number 8 on your own. So for number 8, I'm going to make another table on the side. I'm going to try to do it as quick as I possibly can. So I'm going to come up with some distances, and then I'm going to plug them into my equation to figure out the speeds that they correspond with. So we actually have some from our table from before, so I'm going to pull that back out. When my distance was 12, my speed was 20. When my distance was 27, my speed was 30. When my distance was 48, my speed was 40. And so I already did the work for all of these, so I'm going to include these on my table. And then we can probably include a couple more. So I want to do, let's do like 100 for distance. Let's do 500 and 600. So now, since I have distances, I'm going to plug them in for d here. So I have the square root of 100 divided by 0.03, and I get 57.7. I'm going to save myself some time and just copy that down and change 100 to 500, round that to 0.1, and then same thing for 600. So now that I have points, I can plot them on my graph. My input is distance, so I'm going to label my x-axis as distance. And my y-axis is my speed. I'm going to label this as 100, 200. So I'm just going to go by like 50s there. And then I'm going to go by 20. So 20, 40, 60, 80, 1, 120, 140, 160, 180, 2, and I don't have anything over 200. So I'm just going to plot these points here. These lower numbers are kind of hard because they're so close, but I'm going to do my best. $192 is just under 200, and it goes up to 80. 300 is 100. 100 is about 50. It's not perfect, right? It's just a sketch. And then about 141. So my graph looks something like that. So my domain for this one is talking about my distance. The lowest is 0 and the highest is 1,412.67. That is the same maximum distance from before. It just was listed as the range, not as the domain, but we're still talking about distance. My range would be from 0 to 217 because my range is talking about my outputs or my y values or my speed for this, my lowest speed and my highest speed. So I have my range. My intervals of increasing or decreasing, just like before, it is increasing across the entire domain. I'm just going to write it a little differently this time so you can see the two different ways. So I'm going to say increase over or across the interval, and I'm going to write the interval for the domain. So it's increasing over 0 to 1,412. My minimum is still 0, 0, and my maximum is my maximum distance paired with my maximum speed. So looking at number 9, what do you notice about the graph of S compared to the graph of D? So this graph right here is our graph of S. Let's actually label that. And then I'm going to show the graph of D. So this is our graph for our distance. And I actually want to put them on the same graph so we can make some comparisons. So I'm going to do a little sketch here. If this is my coordinate plane, my graph for S looks something like this. So this is S, the one right up here. And then the graph of D looks something like this. And so if I sketch in my line y equals x, it would go right there. Y equals x is this dotted line. And I can see that if I were to fold my paper on this dotted line, my two graphs would line up. They are reflections across that line. So here we're going to say they are reflections across y equals x. And so thinking back to our lesson 1, part 2 that we did on Monday, if there are reflections across y equals x, that means they are inverses of each other. So they are inverses. We took our table and we flipped our inputs and outputs. Our labels switched our inputs and outputs. And so they are inverses. So number 10 says consider the function d of s over the domain of all real numbers. So that means we're not just looking at like quadrant 1 of our coordinate plane. We're looking at negative x values too. How does the graph change? And so I'm going to sketch that a little bit. If I sketch d of s, so d looked like this. If I extended it to the negative side with negative x values, it would be a quadratic. And it would look like that. And so our domain would no longer be from 0 to the 1412 because we would have to include our negative values. So let's go ahead and flip the page and look at number 11 on page 17. So number 11 says, how does changing the domain of d of s change the graph of the inverse of d of s? So on this coordinate plane, we're going to draw in like an actual coordinate plane. I'm going to use this green highlighter as my axes. And so we have d of s look something like this, which is kind of a rough sketch here. And then our inverse, or our function for s, looked like this, which means it would look like this. Ooh, gosh, this is not very accurate at all. But what that means is I still have my line here for y equals x, and I didn't do great on the sketch, but they should be reflections over that line. And so it changes the graph of the inverse because now I don't only have this piece, I have this bottom piece as well, which is a problem because if you look at number 12, is the inverse of d of s a function? So if I label this pink graph is this, or I could say it's the inverse of d. Is it a function? It's not. When I have a graph and I'm looking for a function, I want to do my vertical line test, which is if I have a graph, if I can draw a vertical line anywhere and it crosses more than once, it fails the vertical line test. So looking at my pink graph here, if I draw a vertical line, it crosses or hits more than once, it fails. So it is not a function. So is the inverse a function? No. It fails the vertical line test. And so something I want you to add for number 12, this is going to be a new vocab word, d of s, so our purple function here, and then we did the inverse in the pink. We would say it is not invertible. So that invertible is going to be a vocab word. D of s is not invertible. We're going to put a definition for invertible at the end of our key points. So let's look at some key points from this lesson. So characteristics of functions and their inverses. So the graphs are reflections over the line y equals x, and we can see that here. My graph got reflected. The equations have the inverse operations in the reverse order. So we saw that, I'm going to pull out a previous page. We saw that when we were solving D for S, we did the opposite operations in reverse order. And then the domain of our function f is the range of the inverse of f, and then the range of f is the domain of the inverse of f. Because what we're doing when we do the inverse is we take our x values and we flip them to our y values, and then our y values change to our x values, and so we're just flip-flopping our domain and range. If I know the domain of my original, I know the range of my inverse. And so the inputs and outputs of the tables are switched. There's one more thing on the back that we're gonna look at. So let's look at page 18. Characteristics of functions and their inverses. So a quadratic function, we were given a quadratic function here for D of S, this purple one. A quadratic function is not invertible, there's that word, unless the domain is restricted to be only one side of the parabola. So let's add a little definition here for invertible. So invertible means that both the function, so the original function, and its inverse are considered functions. So both would have to pass the vertical line test. So invertible means that our original function obviously is a function, but also the inverse would be considered a function. And when we looked at our graph in number 11, the inverse did not pass the vertical line test. It failed, which is why we would have to restrict our domain to just be 0 up until that maximum value, because we don't need this bottom part. Otherwise, it is not a function. It is not invertible.